Thank you.
Good morning, ladies and gentlemen. We still have quite a few folks signing into the meeting, so we're going to wait another minute or so before we kick off. Okay, ladies and gentlemen, it's 10:02, so we're going to go ahead and get started. There'll probably be some late joiners, no doubt. Thank you all for joining us this morning for this presentation. My name is Bert Loving. I'm with AC Controls. Presenting for us today will be Matt Lindo. Matt is our Director of Sales for the eastern portion of the U.S. For Samson Controls. very experienced individual in the control valve world. So we have a lot of attendees today. I would ask that each of you please make sure your microphones are muted and go ahead and turn your cameras off while we're giving the presentation. If
Hey, Bert, you there? I think we lost you.
You're muted, Bert.
Yeah, sorry about that. My microphone is muting itself for some reason. So anyway, without further ado, Matt, go ahead and take over and start your presentation.
All right, thanks a lot, Bert. As Bert said, my name is Matt Lindo. I live around Nashville, Tennessee, so not too far from most of you, relatively speaking. I have about 13 years experience in the control valve industry, worked for a few different manufacturers. And so I've got to be a part of a lot of different types of designs, but also have seen that, you know, when it comes to a mechanical control valve, there are a lot of things that you typically wouldn't think about. When I got my metallurgical engineering degree and decided to go work for a control valve company, I thought, how in the world could this be so difficult, especially when trying to explain it to others? But in my 13 years, I have seen there's a lot to control valves, and hopefully we'll cover some of that today so that you can, first of all, appreciate control valves and the sizing and selection process, but most importantly, so that you can size the proper valves and select the proper valves so that your plants or your customers' plants can run efficiently. Cover a few different basic, let's see if I can get this.
Matt, you muted.
Yep, so mine's doing the same thing. For some reason is muting automatically. We're going to go through an introduction. I'm going to show you a few pictures about Samson just so you can get a feel of control valve assembly and that type of thing. And then we're going to go through some sizing. We're going to talk about the valve flow coefficient, CV, and we'll kind of get into the science there and fluid dynamics. And then we're going to go through a sizing example. I will show you our internal sizing program, and you can really see how this all fits together. And then we'll conclude with a few slides about control valve selection. We'll talk about the three main types of control valves: butterfly valves, segmented ball valves, and globe valves. And then we will go through some selection guidelines regarding those valve types. Okay, so Samson is about an 800 to a million to $1 billion company. We are one of the big four that you typically hear of when it comes to control valves and having the full breadth of product. As you're going to see today, there's a lot of applications. Control valves are really in all industries, and Samson covers the majority of those applications. We were founded in Mannheim, Germany in 1907, and we are headquartered in Frankfurt. Our headquarters in Frankfurt, Germany spans across 36 acres and 1.6 million square feet of building space. We would love to host you at any point if you ever go to Germany for any reason, or if you'd like to go over there. And if you're a control valve nerd like I am, you will be extremely impressed with the facilities, with the manufacturing and testing capabilities. And again, I think you'd understand that there's a lot that goes into the design and manufacturing and testing of control valves. We are headquartered in Baytown, Texas, here in the U.S. We came to North America in 1983 and have been in the U.S. since 1992. And there in Baytown, those are our two buildings. One is kind of for our accounting people, sales people. The other one on the left there is for our production folks. Here's a couple pictures of our facility. This is just a portion of our production facility. As you can see down in the lower left, those are some valve bays. Those are some globe valves being assembled. We would, of course, assemble those from scratch. And then as you move to the right, we have all of our inventory that would be used to meet your lead time demands. And this would be very typical, these bays, for control valves, so you can understand throughput. In that picture on the right, you see the valve portion is in that vise, and we've started putting on what's called the yoke. That's that portion right on top of the valve. And over there to the left, if you look in the lower left, that would be a positioner. We'll talk about all three of those components today because they're all very important when you're talking about control valves. As I mentioned, really any industry that you talk about, anywhere where there's going to be a fluid in a pipe that needs to be controlled, there's going to be control valves present, automatic control valves present. And Samson has solutions for all of these industries. And I'm assuming we have a number of industries represented here today. But really, when discussing control valves, I think we're going to touch on things that are applicable to all of us.
Yeah.
As I mentioned, yes, sir? Okay, someone must have just come off of mute there for a bit. As I mentioned, when you're considering control valves, you really have to consider a complete control valve assembly. This is just a depiction of the different things that Samson manufactures, and this may be the case with a number of control valve suppliers. As you can see in that top portion, the control valve itself, and then that middle portion is the actuation. Pneumatic, electric, electrohydraulic, manual actuators, whatever the case is. That's a picture of a Scotch yoke on top there in orange. That's a rack and pinion actuator on the left. And then a spring and diaphragm. That shows a picture of the casing. There's diaphragm and springs inside of there. And then the accessories on the bottom. So whether it's a positioner or a simple I to P that's taking a current signal and converting that to a pneumatic signal that will then go to your actuator. All these different accessories, all the valves and actuators. One thing that's interesting about Samson is that we manufacture all of our own components, even down to our own screws we will make. We even manufacture our own rubber diaphragms and plastic components. So we have extruders so that we can make all of our plastic components. Quality is extremely important in controlling that whole process. So that's the case with Samson. Now this is just one last slide on the introduction. Whether you're considering different applications, different material requirements, or different testing requirements, our solutions will cover all of those. And this kind of gives you a feel when you're thinking about selecting control valves, all of the things that can come into it. So talking about applications, understanding, is it corrosive? Is it erosive? What are the material requirements? Anytime we get a call, AC Controls or Samson, and you all are saying, I have a valve and it's wearing out and I need it replaced, and you tell us I want a 2-inch class 300 valve, there's probably going to be a number of questions that come from us. And after today, maybe you'll get a feel for why those questions are asked. But for example, anytime a valve's being replaced quickly, let's say it's a 3-month lifetime, I'm going to want to understand what is your fluid, what type of problems have you been seeing, so that we can avoid those in the future. Because from a material selection standpoint, we could maybe give you a more reliable solution. And then on the testing, you're probably familiar with some of those. You see ASME B16.34, that's the design standard that control valve suppliers would use for flange, threaded, and welded end valves. That tells you things like pressure, temperature ratings, and dimensions for designing the control valve. That ANSI FCI 70-2 up top there, that's for leak testing. So then we would test according to that standard. so that we can understand if we're meeting the max allowable seat leakage. You've maybe heard of class 4 leakage, for example. Well, that's the test we'd use to run and make sure that our valve, as it leaves the test stand in our facility, would meet that standard. And then ISO 15848, that gives you another flavor of the testing that could be required. That would be a fugitive emissions test based off of a shell test. All right, so let's get into it. This is a very basic slide, and many of you may already understand this, but there may be some on here that are kind of new to control valves. Again, this is just pointing out that when it comes to a quote-unquote control valve, you're actually talking about a control valve assembly in most cases, which has three main components, three basic components. And all three of these components are incredibly important and necessary to understand when you are selecting a control valve. So you have the valve, they're depicted on number 1 and pointing down to that lower portion. That's the component that is really where the rubber meets the road. That's going to have your orifice or your seat and your plug, and that's what's going to be controlling that process variable or manipulating that process variable. Then number 2, that's pointing up to the actuator. So as it states, this actuator is going to translate the output signal of the controlling device into an actual force that moves that valve that we just talked about. In this case, this is a spring and diaphragm actuator. So you put air on one side on the diaphragm, and that will oppose the springs. And then those springs will also provide an inherent fail position. And so that's the actuator that provides the force to the valve. And then number 3, there's commonly going to be an instrument. Most of the time it's mounted right on the valve assembly. In this case, it's a positioner. That instrument receives the signal from the control system. 4 to 20 would be very typical. It takes that 4 to 20 and translates it into a pneumatic output into the actuator. Then the actuator moves the valve. And what a positioner does, it is connected to the stem. You can't see it there, and you'll see a slide at the end of this presentation why that is. But it's connected to a stem so that it understands if it did what it was supposed to do. So if it takes a 12 milliamp signal and you're expecting the valve to get to 50% open, that positioner will understand and then do whatever is necessary to get to 50% open, as opposed to an I to P, just a basic I to P position transducer. The I to P wouldn't know if it did what it was supposed to do. It just converts a incoming current to a pneumatic output, and it has no feedback connected to the valve. So why do we size and select control valves? Just so we don't make it chaotic and people coming off of mute, I'll just give you the answer. Typically in the past, valve selection has been based on, a few basic things, like the customer simply requesting, I need a control valve for some obvious things like I have a budget of X, or I need whatever delivery, or my line size is 2-inch, so give me a 2-inch valve. But that really isn't the most appropriate way to size and select valves. Just like most of the things you do when you're selecting equipment in your facility, there's really a few goals in mind, and that's to reduce process variability, to increase plant reliability, and to increase overall plant efficiency. And if you're going to do all 3 of those things or meet all 3 of those goals, you have to have properly sized and selected control valves. So I have 3 different reasons why we take the time and actually size and select proper control valves. Number 1 would be economics. Everything we do is tied to money. And so you can think of this in a couple ways. Number 1, the manufacturer, when you're working with them and you're working back and forth, you're really trying to find the smallest valve possible and really the least expensive valve that is going to be able to accomplish what you want it to accomplish. Many times, if you come to us with a 4-inch line, you may get a recommendation for a 3-inch or a 2-inch control valve. Again, economically speaking, we could have used a 4-inch valve. There's probably a 4-inch solution that will work, but you can save money by using the 3-inch solution. And then also from an economic standpoint, you take the time to size and select so that you have a reliable solution that's going to last you. And of course, you think of economics across the entire life cycle of the control valve. There's the initial capital expenditure and then the ongoing maintenance. So understanding all of those things, to take the time to size and select, to go through all of these questions that you're going to get from the manufacturer, you're going to get the most reliable solution. Secondly would be controllability. You're obviously looking for a valve that can actually control the process variable that you're trying to control. And the valve, remember, is really where the rubber meets the road, where this is happening. And so if you don't get this right, then you're not going to be controlling the process, or the process output is not going to be what you're looking for. And when you go into a typical plant, I found this often in the oil and gas industry. I used to live in Colorado. A number of the valves were undersized. A lot of the valves were just wide open because they cared about throughput. They wanted to process as much gas as possible and get paid for it. And so when it came to sizing and selecting, their process really wasn't running as they originally had designed or intended. So you'll see a lot of valves either undersized or oversized because now the process is running differently. And so the valve really isn't being used as originally intended. And then my last bullet, the right valve for the best performance. This would just cover a lot of other areas. Understanding if you have the right valve for the right application, back to how we discussed there are corrosive media, erosive media. What are your shutoff requirements? If you don't have isolation valves and you need the control valve to have a certain shutoff, selecting that. All of these things come into play as to why we size and select control valves. All right, so let's talk about control valve sizing a bit. We're going to touch on really just the first of 3 main categories when it comes to control valve sizing. I would classify them as general applications, as critical applications, and as severe. Critical being it's critical to your process. Severe being, did someone take over? I didn't touch a single thing. It looked like someone took over, and then so it took the sharing from me. So I'll reshare my screen here. Someone started a recording, and so then it did that. That's what it said. All right, let's see. Can everybody see that?
Yeah.
We can see you again.
Yep.
All right, nobody do that again. Okay. Okay, so we were talking about general. So we're going to keep it very basic today, and then you'll get a feel and be able to then understand severe applications a little bit as well. But this discussion could take hours. So we're just going to focus on very general applications. And again, I'll show you some examples here in a bit. So whether you are dealing with a liquid or a gas, these are the different process variables that would come into play when sizing a control valve. Today, we're going to focus on just liquids. So as you can see, for both liquids and gases, upstream pressure, downstream pressure, flow rate, and then the fluid characteristics or properties, the temperature, and as you can see in the gas, there's also a compressibility factor that is taken into account. So this would be the type of information that you would be asked by a control valve supplier. We need this info in order to size a valve, and here's why. So in looking at a liquid, we're going to stick with just the variables in the basic liquid sizing equation. When you size a valve, you can't just simply use this basic equation. There are actually numerous factors that go into the ANSI IEC 60534-2-1 standard. You can read that standard if you want to at night. Things like liquid recovery coefficients and accommodations for valve geometry, like different valve styles and trim types will have different variables that go into the equations. And then things like swaging factors for piping. That's why we need to ask you what your pipe size is. Well, all of that summed up really comes down to this basic equation that you see here. So basically speaking, the flow rate is equivalent to the valve coefficient, or CV, times the square root of pressure drop. And that is assuming a specific gravity of 1, which would be water. And as you can see in the depiction, you have an upstream pressure P1, an orifice which has an associated CV, and then your downstream pressure P2. For that CV of that orifice, you can then calculate what flow rate can I pass through this CV at this given pressure drop. How I like to think of it is really flipping the equation around. So if you come to me with these process variables, with flow rate, with your fluid type, so that I know specific gravity and vapor pressure and those sorts of things, and then your pressure drop across the valve, I will then use that information to calculate the required CV. How much area or space do I need to accomplish the process conditions in this process? CV is a unitless number. So 1 CV is equivalent to 1 gallon per minute of water at 60 degrees Fahrenheit and a 1 pound pressure drop. So this CV it represents the area, or you could just say the capacity, in order to pass that flow rate at that certain pressure drop. So hopefully that makes sense. And in this case, I'll just ask a quick question to see if you understand. If my fixed area or fixed CV remains constant, if it's like an orifice plate and it remains constant, and I want to increase my flow rate through that capacity, through that area, through that fixed CV, what has to happen to my pressure drop in order to pass additional flow rate? Well, the pressure drop would have to increase. So even more basic than the equation you see on top there, you can essentially conclude that CV is equivalent to flow rate divided by pressure drop. And you're going to see in our example how that's pretty close to accurate. CV is equivalent to flow rate divided by pressure drop. When it comes to control valves, the point is that the control valve is capable of a wide range of CVs, a wide range of capacities. It can move to barely open all the way to, 100% open. In this case, on this chart, this valve is capable of a CV of 10 at 10% travel, all the way up to a CV of 1000 at 90% travel. That'd be a turn down, a controllable turn down of 100 to 1. And so that's the point, that this control valve can cover a wide range of process conditions. Because typically when you're going to have a control valve, that's the point, is you're going to have a number of pressures or flow rates, whatever the case is, and whatever you're trying to control. And this valve is capable of covering all of those process conditions. And not only does the valve literally move and have different capacities, but it's also been designed accordingly. You know, with the guiding and other features, it's designed so that it can actually throttle and do it smoothly and then be reliable and not wear things out. Here's kind of a nerdy chart that may bring back some memories, especially for the engineers that are in this call. If you remember Bernoulli's law or Bernoulli's principle, as velocity increases, pressure will decrease. Well, the control valve is a restriction. And so with that restriction, you're going to have an increase in velocity. And then according to Bernoulli, you'll have an associated decrease in pressure. What this is showing is just to remind you that inside of that valve, even though you know your P1 and P2, the upstream and downstream pressures, inside of that valve, there is a lot going on from a fluid dynamics standpoint. Because of that restriction, there's a point at which your velocity is highest. And at that same point, look at that profile, your pressure is going to be the lowest. So one thing I'll point out, considering these things, we don't have time to talk about all of the fluid dynamics, but one thing to point out, back to the general versus severe applications, if you have a situation that your velocity increases and your pressure decreases in a liquid, that pressure may decrease below the vapor pressure, and thus your liquid becomes a gas. And then if it recovers, as you can see in that profile, every valve is going to recover a certain amount. That pressure recovers back to P2, that gas may implode back into a liquid. Many of you may know what this phenomena is called. That is referred to as cavitation. So your pressure inside of the valve decreases below vapor pressure and then recovers back above the vapor pressure and becomes a liquid again. And that cavitation can be damaging. So when you bring us a set of process conditions, you may hear back from any valve supplier that, hey, we see this as potentially cavitating, and we need to handle it accordingly back to the reliability to give you a reliable valve. And you've probably heard of cavitation with pumps commonly. So that's just a little bit about fluid dynamics to know that there's a lot going on inside of that valve because of the restriction. This is a screenshot of our sizing program. We refer to it as CSAM. And you remember these process variables that I mentioned a few slides ago on the left for a liquid. Those would be the inputs. So really the goal is to input these process variables, understand what you're trying to accomplish, calculate a required CV. That's about halfway down. You can see on the left, 169. You calculate a required CV, and then you select your valve that has a rated CV capable of controlling that required CV. So from a sizing perspective, that's really the goal. So let me bring up a sizing example to show you. Can everybody see that?
No, not if you have the sizing up.
Okay, let me move it here. What about now?
Not yet, just the PowerPoint screen.
Okay.
I think you have to reshare a different screen is how it works on here.
Yeah, let me try that. All right, here we go.
Hang on, let's see.
You see
There you
that?
go. Yep.
Okay, so this is that sizing program. So I've just put in a basic application here. 150 GPM, Q is my flow rate, 400 PSI upstream pressure, 250 downstream pressure, and 90 degrees Fahrenheit. And so when I calculated this CV, if you scroll down to the valve results, you can see 12.2 CV required. Well, this program automatically selected the appropriate control valve. In this case, it was a 2-inch over to the right. If you look at that valve, it was a 2-inch, 300-pound, and this was a globe valve, and we'll talk about that in a little bit. And the CV about halfway down, you'll see the CV is 20. So this CV for this specific valve of 20 will handle the required 12.2 CV. And so now I'm going to input a few other inputs just to show you what happens in a few cases. So considering the same flow rate of 150 GPM and the same inlet pressure of 400 PSI, now I'm going to include a lower downstream pressure. So my pressure drop is going to increase. So back to the simple CV equation, CV equals flow rate divided by pressure drop. My CV required should go down. But we're going to see something else happen if this in fact were a realistic condition in your process. So I'm going to hit the calculate button. So you saw my required CV went down to 8 from 12.2. We see this warning here. I thought it was maybe going to warn me and say cavitation. You may get a warning from your vendor that says there's cavitation. Now, because of this severe pressure drop, we're dropping below the vapor pressure of the liquid. And so in this case, it says that there is hardening required. And so any manufacturer is going to understand what is the degree of the cavitation, what's going on inside of this valve, and then how much do I need to combat that. When there's severe service discussions, we could talk about ways to get rid of that cavitation to ensure that it doesn't happen inside of the valve. But one of the first ways is to just withstand the potential damage associated with that cavitation, in which we would harden the valve trim to give a more reliable solution. And then let's look at one more condition. If we were to triple the flow rate in this condition and back to the original pressures of 400 upstream and 250 downstream, considering the simple CV equation, what do you think is going to happen to our CV? CV is equivalent to flow rate divided by pressure drop, essentially. Pressure drop staying consistent, our flow rate triples. Our CV is likely going to approximately triple in this case. Let's see if that's the case. It's gone from 12.2 required CV to 36.7. So for our first two conditions, a 2-inch valve was appropriate. And now we have to move to a 4-inch valve. This 4-inch valve can cover all three conditions. So let me bring this up quickly. Hopefully you can see this screen. So a required CV all the way from 8. Can you see that screen?
Yep.
If I go to globe valves, this is Samson's website. This would be the case with any control valve supplier. And you go to the data sheet, you can check that sizing. So my CV required was 8 to 36.6. Here in table 3.2, we go to this 4-inch valve, and it can cover up to 190 CV. And you can have a reduced trim that will have 75 CV. So the 4-inch valve from a max capacity standpoint is appropriate for the 75 CV. Now, if I go back to my sizing, you'll have what's called the sizing curve or the valve characteristic curve, and it'll show you where these conditions land for this specific valve. As you can see, our condition 2, which was our minimum CV required, we're handling that at about 36, 37% open. And then the max condition, condition 3, is at about 82% open, which is ideal in a globe valve. A globe valve, you really want to control between 10 and 90% open. So in this case, we have a one valve solution that can handle all three conditions. All right, so I'm going to pull this back up. We'll see what happens. Can you see that screen?
Yep.
Okay, good. All right, so we've talked about sizing, calculating CVs, and then selecting an appropriate valve accordingly. Now we're going to talk about some other things when it comes to valve selection. So this is that same screen, and if you notice over to the right, that's where the appropriate valve was selected. So we'll ask you for process variables. That's to calculate a CV and select appropriately. But there's a lot of other things that may come into play in selection. How much space do you have? What face-to-face considerations are there? What is your pressure and temperature so I can have the right ANSI rated valve and handle that pressure and temperature with my min wall thickness? Is there a flow characteristic? Is it a critical application where your control systems folks and process folks have said, I need to have an equal percent characteristic to line up with my control system properly? Is there specific trim and body type and size requirements? So not only the face-to-face space, but do you have height restrictions that need to be taken into account? What is the control system? And what is the communication protocol? Is it a field bus system or a HART system, which would be typical? Because that instrument that we select is selected accordingly. What is the supply medium? So most of the actuators you've seen depicted so far are all pneumatic actuators. So that's assuming a supply of air is present. Well, what is the pressure? Because that has to be used to select the actuator. And then also, what performance are you looking to get? We'll know the rangeability required when we calculate the CVs, but you may provide other communication that says, well, that maximum condition, I don't really need to control that condition. That can be handled if the valve's wide open. And in fact, if you select a valve with a certain CV, just tell me the wide open flow rate and we can live with it. So we have to have the discussions around what performance are you looking to get out of this valve? So what makes a good control valve? There's a lot of things mentioned. You can probably come up with others. Of course, you want high quality, well-engineered equipment, but then things like your design, the flow geometry and the frictions inside of the packing and the sealing. Is it going to keep the product in the pipeline that your safety folks want to stay in the pipe and in the valve? The controllability, how well can it control? Most positioner manufacturers will tell you how well that positioner can control. How does it respond to step changes, or how quickly can the assembly open if something fails and it needs to go into its fail mode? What's the ease of maintenance? How easy is it to work on? How easy is it to commission and to calibrate? So beyond just sizing the valve and understanding if it can cover a CV, there's a lot of things that go into the selection process. Diagnostics. Do you want the valve to understand its own health? And then you can monitor that so you can prevent maintenance in the future. Scheduling. If you come to us and say, I want the best valve I can get for here's my application, we will give you the best valve according to sizing and selection. But if it doesn't meet your schedule, if you've got a shutdown in 3 weeks, that's going to have to be taken into account. In most cases, a process can be handled from a number of different valves, even different valve types, which we're going to discuss on the next slide. And so looking into these other things like economics, the reliability you're after, the control you're after, and the schedule, then we can hone in on the appropriate valve that meets all of those things. So in general, there are three different types of control valves: butterfly valves, ball valves, and globe valves. This chart shows a CV versus price. So a butterfly valve in general would have the highest capacity, and then a ball valve, and then a globe valve depicted in the black line. And for a given application, you may commonly think of a globe valve as the appropriate solution. Let's say it's an 8-inch line and you need an 8-inch globe valve to meet that CV requirement. Well, you may have been able to use a 6-inch ball valve or a smaller butterfly valve, or even a line-sized butterfly valve that can still control that condition and save you money. So let's talk about each of these valve types and the different things to consider, some of their positives and negatives for each of the valve types. So for a butterfly valve, you probably have a lot of butterfly valves in your facilities or your customers' facilities in on-off applications, which where they're most commonly going to be used for. But in a control application, there are butterfly valves. That's where the phrase is high performance or a double offset butterfly valve. And in this case, this is a triple offset valve depicted, where it's designed to have the ability to control as well. For a butterfly valve application, you want to probably stay between about 30 to 70 degrees open. Outside of that range, it's going to be very difficult to control. If you can just imagine this big disc in the way at 20 degrees open, a very small input, change in input signal, is going to result in a large change in your flow, because there's a lot of stuff in the way in that application. And so we'd use it for more basic applications. Maybe it's a fairly static process where you're maintaining a flow rate right around 40 to 50 degrees open, and it can be a very economical solution. Some other positives is that it has a short face-to-face, so the space requirements are usually benefited with a butterfly valve. It has high flow capacities back to the amount of CV per dollar spent. It can be a value in larger sizes. But some of the drawbacks with butterfly valves, there's not a lot of customization available. When we talk about customization, I mean inside of the trim of the valve. You can see this trim is just simply a shaft and a disc. When we get to and then there's a seat there as well. When we get to the globe valve, you'll see that the globe valve has a lot more options, a lot of different trim types that can be used for things like cavitation and flashing in liquids, or noise attenuation needed in a gas that's taking a high pressure drop and is going to be noisy. Most butterfly valve manufacturers aren't going to have options to cover this range. And then the last negative there, the third to last bullet, would again be the small control range. So it's not going to have a very high rangeability. But in basic applications, it's something that's missed. So if you're dealing with larger line sizes, back to the economics, it may be wise to think of butterfly valves to potentially save you money, as long as it can control as your requirements state. Then the next valve type would be the ball valve. This is a picture of a ceramic ball valve. You can see the ceramic liner and the ceramic ball. That would be used in an erosive service, also corrosive, but typically an erosive service application. We'd select ceramics if every other type of material is getting beat up because of the erosion. This picture, as you can see, it's a ball that's going to open, and as it starts to open in this cross section, it has a smaller CV, and then as it opens more and more and more, it'll have a larger CV. So there's a characteristic in that ball. Most of the ball valves in facilities would have a V notch, which is intended to do the same thing. That V, as it barely starts to open, is going to have a smaller CV. and then it can open all the way and have a very high rangeability. So the control range in a ball valve, the rangeability is going to be more than in a globe valve. So that's one reason you may go from a globe valve that we're going to talk to you about next to a ball valve, or that your process conditions are just outside of the range, the capability of a globe valve, and I could potentially save money by using a smaller ball valve. They're very flexible. They can be used for a wide range of applications, basic applications to severe service applications. They're very commonly used in pulp or slurry type applications. They have a high rangeability, but they are limited. So they don't have as much flexibility as a globe valve. There are some cavitation and flashing solutions, but it's limited. And it's really just going to be one option, and it may not reduce cavitation or noise attenuation as well as a globe valve solution would reduce. One thing to consider with ball valves is a lot of manufacturers have limited pressure drops that the ball valve is capable of handling, whether it's the design or that pressure drop and calculating torque requirements, and it's hard to find an actuator. If you did have an actuator, the output of that actuator would snap the shaft or the bearings. So there's some limitations from a pressure drop standpoint. Most of you, when you hear the word control valve, are probably thinking of this globe style or linear style or sliding stem style valve. That's really the bread and butter control valve in the control valve discussion. It can handle a lot of different applications. Clean fluids, sticky or gritty fluids, again, because you can change to a different trim style to handle those different types of fluids. It can handle a high pressure drop while still maintaining tight control. It has a good range, not quite as much rangeability as a ball valve, but it will control very well across that entire range. You can still get tight shutoff. So one of the benefits of a butterfly valve and a ball valve selected appropriately are the shutoff in a soft seat. You can still maintain good shutoff in a globe valve as well if you select the appropriate trim. In this case, I've noted an unbalanced trim. You can still have tight shutoff. And then there's a lot of different trim solutions. I've got a picture in a couple slides to show you the various amounts of trim. If you remember when I went to that bulletin, the Samson bulletin, when we were looking at CV, some of those sizes of valves had 10 different trim sets that could be dropped down into the valve to give you very good control and zoom in right on the required CV so that you're controlling in the optimum range, 40 to 50% open. I'll skip through this slide. This just goes to show that there's a lot of discussion in sizing and selecting valves, and it's a team effort in order to be successful. So this is a picture. I've got just a few more slides. I want to give you a couple examples regarding selecting a globe valve and then selecting a rotary ball valve. This just shows all the different types of globe valves that a typical manufacturer is going to have available. That one on the upper left, that would be a microflow style valve. That's the Samson 3510. That's for small CVs. That valve is a bar stock valve for very small CVs. That fully stainless valve, that second one in from the left, that would be for hygienic or sanitary applications in a food and beverage plant, for example. That valve on the bottom, that has a liner, a PTFE liner. So if you have a corrosive application, you may be able to select a valve that handles the CV, but if the metal's going to corrode away, or if in order to handle that corrosion, you need to use a Monel or a Hastelloy or some other high alloy, you may be able to save money by using a lined valve, a ductile iron body with this PTFE liner. That's the Samson Pfeiffer line. Then you see that angle valve, if it's piping requirements that require an angle valve, or if that's a flashing application and you want to flash down and have a liner inside of the valve that's sacrificial that then you can remove to maintain the integrity of the body. That's an option. And then that one on the far right, that's a cryogenic valve. That's a top entry valve, specifically for a gas separation application on a cold box. That would be used. So because of temperature, we need to get the packing and the instrument and everything away from that temperature. And so we have that extension bonnet. This is just to show you the internal design of a globe valve. You can see the seat and plug in the bottom. Your manufacturers, when they're looking at your application, they'll try to match CV, but they'll also understand the guiding that is going to be necessary, those guides, and then this trim type. Should there be a cage? Should it be a cage retained seat or just a screwed in seat? All of these factors go into play even once you've decided a globe valve is appropriate. Here's a picture of some various trim styles. All of these trims could go into the same globe valve. That one on the upper right, that would be that pressure staging to ensure that cavitation doesn't happen inside the valve. Same with that lower left. But as you can see, there's a lot of different trim styles. And then let's talk about one thing with rotary valves. So this is a picture of some different rotary valves. Ceramic valve in the lower left, aligned butterfly valve in the upper middle. That's your typical segmented ball valve in the middle on the bottom. Commonly, you'd move forward if the rangeability required it, or if you've been using that face-to-face and you're replacing that same face-to-face, you'd move forward with a segmented ball valve. But one thing to consider in sizing and selecting rotary valves is that ball rides on the seat the entire range of motion. So it can sometimes be a maintenance hazard if the application is a little more severe and you have to replace seats often. Even when considering rotary valves with that same face-to-face, you may be able to move forward with a double offset ball valve, or this is a plug valve, where the plug comes off of that seat as the valve begins to open and your reliability increases. And the valve moves very easily and controls very easily because you don't have the friction of that seat. So even when you've spec'd rotary valve, there's different valve styles to consider that is going to increase your reliability and controllability. Then this is my last slide in considering sizing and selecting control valves. This was just a basic overview. I hope you learned something today to add to the arsenal so that your plants can run more appropriately in the future. So we haven't talked a lot about actuator sizing. That's a whole nother discussion. But I did want to touch on positioners. So in selecting the appropriate positioner or the appropriate instrument, this instrument is most commonly going to be mounted on the control valve assembly. So just that alone is, you have to understand, is this instrument capable of being mounted on this assembly? In this depiction on the far right, you'll see a cross section. You'll see our positioner mounted on the valve. This is an integral mounting where the positioner is mounted directly on the valve and it just slaps straight onto that box and the air comes out of the back of the positioner and straight into the actuator without any tubing. And it's very easy to mount. Back to the commission and calibration requirements. This positioner is very easy to mount on the assembly, and then it has a push button calibration and that local display. You don't need a handheld in order to do that. And of course, we can handle all communication protocols, Profibus, Fieldbus, HART. So these are just the various instruments. That one on the right, that's our supply filter regulator. So you'd have that instrument ahead of the supply that's coming into the positioner. There's a picture of a solenoid, picture of an I to P, those lower two pictures. That's just taking a current and converting it to an output, pneumatic output. So the instrument is part of the selection process as well. All right, does anybody have any questions? I don't know how we want to do this, but I guess just speak up unless Bert had a different idea.
No.
There is one thing.
Go ahead.
I was going to say, hey, Matt, this is Blake. I was going to say there is a question that was posted on the meeting chat if you want to address that one.
Okay, can someone read that? My screens are both taken up from PowerPoint. Could someone read that question?
Yeah, I'll read it for you. Hold on. It says, our plant process has 50% turn down ratio and good set point control is important. We operate about half the time at 50% and the other half at 110% flow rate capacity. How do we choose minimum and maximum flow rate capacities for the valve selection and sizing?
Okay, so if I understand it correctly, the majority of the time they're operating at one condition and then they're at 110%. So let me answer that a couple different ways. So we'd want to know what are you going to use as your normal case? What do you need the valve to be most reliable in handling? And then is that maximum? Again, are you okay with the valve being wide open at that maximum case? And if the flow rate is around there, are you fine? We would want to do what's called the bracket method. If you remember when I pulled up that sizing, we'd want to know all your different conditions and then ensure that we have a valve that can handle the min and the max. The min condition is going to come from your lowest flow rate and your highest pressure drop. And your max condition is going to come from your highest flow rate and your lowest pressure drop. So I would size that valve to run at probably 40 to 50% open to handle that 50% case that you mentioned. And then choose the right rangeability for my valve type to also handle that 110% max case. So that'd be 110. If it's the same pressures, then a globe valve should be able to handle that. If you're running at 50% flow capacity and then 2.2 times the flow would be your 110% flow capacity at the same pressures, a globe valve will be able to handle that application. Any other questions?
Here's another question there, Matt. It says, what is Samson's take on the trend to use variable frequency drives on pumps versus using control valves?
I don't like it because then we don't sell any valves. That's the first answer. Other than that, I can't really comment on that process side of things. I'd have to talk to some other folks, but we just design, engineer, and sell control valves. I'm sure there are plenty of applications. I've used them in my past. Use a pump and then a variable frequency to control the output of that pump as opposed to using a control valve. So I guess things like preference and the amount of control required would kind of impact that decision. But I'll leave that conversation up to engineers at EPCs and process engineers and operators.
And Matt, there's another question from David. Are control valves set up to target a flow rate or pressure? What is the common process variable?
They're set up, they can target both. and I guess I couldn't say that one is more common than the other. And there are ways in our positioner to also handle both in the same application. So I don't think one is more common than the other.
Okay, thank you. Another question just popped up. How do you know what control valve characteristic the process requires, equal percent or linear?
Well, based on my experience, both will work in a given process. If it's such a critical application that the customer would make that decision, if they need our control valve to, combat something else in their process, if they're looking for an overall linear type process for that specific portion of their process, and they need our valve to supply equal percentage to combat their signal so that they have an overall linear, they would have to tell us that. There are some applications where we take into account if we want to quickly lift off the seat, then maybe we'd select a certain characteristic. And also those characteristics result in different CVs at various openings and even different maximum CVs capable. So we take that into account when selecting the characteristic. John, or anyone else? John or Bert, do you have anything to add to that, or Justin or Sam, Blake?
Yeah, I don't. I think you covered it. It's generally a process. Generally a process condition that determines that, or perhaps a control system condition. So I don't see any other new questions. Going once, going twice. If not, then thank you all for attending. We're going to go ahead and shut the presentation down. We did record it if there's anyone in your organizations that might want to view it at a later date. Thanks again. Have a safe day.
Thanks, Matt.